Simulations and systems in general are becoming more and more data-driven. This can be as simple as flying a plane in a flight simulator with the current weather conditions and surrounding air traffic. Modern simulations are getting more complex depending on data from different simulated sources as well as live data. To connect all those devices together, a common understanding of the data model, or transformation between the different interpretations of the different data models is needed, as well as a common protocol which the devices can understand. Data Distribution Service, DDS, an open standard from the Object Management Group, is at the foundation of many of today's standards like FACE, the Future Airborne Capability Environment, SOSA, Sensor Open Systems Architecture, RVIZ, Robot Operating System, to name just a few. This makes DDS a prime candidate for a common data bus to connect those standards as well as different devices and applications together. What if we connect some of our demos together? Let's connect applications from RVIZ, FACE, SOSA with technologies like gaming engines and cockpit displays, using a variety of data, high throughput, like video, or smaller ones like position updates. And of course, we wanted something interactive and fun. This is what we came up with, and we already have ideas of more things we can add. We created 2 drone simulators based on Microsoft AirSim using Unity and the Epic Games Unreal Engine. A plugin using the AirSim SDK publishes location, video, and lidar using the SOSA interaction bindings. The lidar data is displayed using RVIZ, a RAS2 application. The position information drives different UIs. The demo uses 4 topics. The topic drone position is used to synchronize between the different drone simulators. The other 3 topics are the camera, lidar, and location update, which are subscribed by the different applications. Let's look at the different pieces. The integration into the Unreal Engine and Unity is based on the example from our Case and Code website. The drone simulator publishes the drone position topic, which is the current position of the drone it controls. Each drone has a unique identifier. Here you see the drone flying in the simulated environment and the admin console on the top left plotting the altitude, which is part of the drone topic. The drone topic is used to synchronize between different instances of the drone simulator. The simulator also subscribes to the drone position topic, and if a drone with a new unique identifier is discovered, it will create a drone instance and the drone will show up in the simulator. Each instance of a drone simulator will show all the drones flying in the same environment. They will automatically be discovered. This allows to share data between the Unity and the Unreal Engine drone simulator. Next, let's look at the plugin using the AirSim SDK. The plugin gets lidar, camera, and position through the AirSim SDK APIs. The information is published as 3 different topics: camera data, lidar data, and position, using the RTI Connext TSS, which is based on the FACE Transport Services segment as defined in the SOSA interaction bindings. In other words, the plugin is SOSA-aligned to publish the data to the data bus. The camera viewer is a standalone application which subscribes to the camera data and displays the video. The lidar data topic uses the RAS point cloud 2 data type, which allows the data to be directly displayed in RAS RVIZ, a standard RAS2 tool. Using the RAS2 data type allows to directly use RVIZ without any modifications. We have a cockpit display application using ENSCO IData. It is developed for planes, so some of the data from a drone may not make much sense. For example, the speed is much lower than a plane would move. The display also has a moving map. The environment we use in the gaming engine is not a real place, so the location doesn't match to anything on the map. but for demo purposes we fixed the center location to the Aspen airport. However, you can still see the map moving as the drone turns. The video data could also be fed into the cockpit display, also not implemented in this demo. We also have a cockpit display by Presagis. The display is designed for helicopters, and as with the previous one, not all the information is applicable to drones. In this demo, we feed altitude, speed, latitude, longitude, pitch, roll, and heading into the display. The rest of the data is simulated. The next display is the Ansys CDS, which is built on the Ansys FACE-conformant A661 server. The display uses its own FACE-conformant data model. Using the Connext gateway, we bridge the location topic we use in this demo to the view topic for the FACE data model used by the Ansys CDS. That way, we feed all the relevant data into the CDS, even though it uses a different data model. Last but not least, we added a Connext gateway configuration, which maps the position data to Google protocol buffers, which is transported over 0MQ. The SOSA interaction binding allow for DDS, as well as Google protocol buffer over 0MQ to be used as transport. We added the gateway to show that we can connect to any SOSA-aligned application. The console window at the bottom shows the Google protocol buffer data.